Okay, so what's next? We talked about what a quadratic function is. It has linear rate of change. We talked about, looked at a table example. We looked at tables with graphs, talked about the vertex, talked about the two types of formulas. There's the vertex formula and the standard formula. They do the same thing. And remember, this is similar to when you work with linear functions and you have the slope-intercept formula, or you have the slope point formula. They do the same thing. Right, but they're nice to have. This is really nice for interpretation when you're looking for the vertex. This is kind of nice to have if you're working when you're trying to when you're sort of solving equations or something. And then we move on to modeling. So modeling is, of course, one of my favorite topics. It's my favorite because you get to create your own formula from a picture, basically, and use that formula to do something. So remember, my 4 steps for solving any problem in the world, or a word problem in a math class, is first we want to draw a picture. So here we have a farmer decides to enclose a rectangular garden with 600 feet of fence using the side of a barn as one of the sides of the garden. Find the maximum area of the garden. So here you have a rectangular garden, so let's make our garden here. You have a barn for one of the sides, so let's say we have a barn on this side. Of course, we'll label the horizontal stuff X, vertical stuff Y. I probably wouldn't label this Y because you don't need a fence here. This is a barn. I have 600 feet of fence. Unless that's not area stuff because it's not feet squared. This is the amount of material I have. And always write down what you need to find. I find that that's one of the most important things to do because we often forget what we're trying to find. So we want to find the max area. These are called optimization problems, and the idea is you find a formula for something, and then we can use a piece of technology, in our case our graphing calculator, to optimize it, to find the very largest or smallest, which we call the max or min. And so for our equation, it depends on what we're trying to find. So we're trying to find the max area, so I'm going to look for an area equation, try to maximize it, or optimize it if you like. So that's x times y, length times width. Of course, I can't graph that because I have x and y, so I need to get rid of one of these, and that's where this number is going to come in. So this number here, 600 feet, is the amount of fence I have. So I can write down 600. I can express it, basically, in terms of x's and y's. So you have 1x, 2x, and 1y. So 2 x's plus a y. Remember, x and y stand for x feet and y feet. So you have x feet plus y feet plus x feet should be equal to 600 feet. You can solve this for y by taking away 2x from both sides. And so what do we have? We have 600 minus 2x is equal to y. And then the idea is we can take this y and replace it with what it's equal to. 600 minus 2x. So a will be equal to x times 600 minus 2x. And now this is a formula that we can graph. And it's a quadratic formula because when you multiply through by the x, you get 600x minus 2x squared. So it's clearly quadratic. But all we need to do is take out our calculator here to solve the problem. So here's our calculator. We want to basically graph this function, so turn it on, hit y equals, and then we're just going to graph it. So you have x, and you have left parenthesis and 600 minus 2x in parenthesis. And then in order to graph it, we need to set up our window. We have to know where to look. So you have to think a little bit. You have to think about what x represents. So x represents the length of this fence. So you can start at 0 for no length. And then you can go up. Now I wouldn't go up to 10 because you have 600 feet of fence. So I might go up till about half of it, or you can kind of just guess and check. But if you do 300, you'll see you get a really nice picture because it's half of 600 and there's 2 x's basically. But you can really just guess and check. And so then we're going to go to zoom and find zoom fit. So I usually scroll down and find zoom fit or 0 and hit enter. Then we're going to get a nice looking graph. Oops. We're going to get a nice looking graph that goes up and comes down. So the input is the length, right, of this fence here. And then remember the output actually isn't y. Remember, it's the area. That's important. All right, so let's copy this graph down to show some work. So now I'm solving, basically. I'm solving this problem. I graph this between 0 and 300. I remember from the picture, my calculator went up and came down. And so I'm trying to find the maximum right here. And what you'll notice on your calculator, if you hit second and then the trace button, which takes us to the calculate menu, you'll see there's actually a maximum button. So you can hit maximum, and then you can just scroll to the left when you think you're to the left of the maximum and hit enter, and scroll to the right, and you can watch it kind of pass the maximum there. And when you feel comfortable, that's the right, hit enter. Then you just hit enter for a guess, and it'll jump right to it. And so on this one, we want to find the maximum area. So you have two choices. You have this x is 150 and y is 45,000. Now remember, this y and this y are not the same y. This is the length of the fence here, whereas this y is our output, which remember is area. So all I really care about is that number there, the max area, is 45,000, and of course it's feet squared. I'm just ripping that off my calculator there. It says 45,000. So this point right here, that point was 150, comma 45,000. And I want the max area, so I want the 45,000. And make sure you put feet squared because the units matters. If you put feet, it's wrong because it's not area. It has to be feet squared. There's no real way to test this problem, although you can go back and you can actually find the dimensions if you want. If you know x is 150, so if you know x is 150, then you could probably figure out y, because y is 600 minus 2 times x, so it's actually 300. If you take 300 times 150, you get 45,000. So, maybe it's right, but it's hard to check this problem. Actually, in calculus, you learn a way to do it without technology, and we often use our technology to actually check if our answer is right. All right. Then the next, so that was a geometric problem. The next type of problem is sort of a table problem, and I enjoy table problems too because you can really see the formula and how formulas actually work. So on this one you have an airline carries 6,000 passengers per month, paying $200. And a market survey indicates for each dollar decrease in ticket price, the airline will gain 50 passengers. Determine the ticket price that will maximize the airline's monthly revenue. So maximize revenue. All right, so I'd like to highlight or underline things, and then I trim down and try to draw a picture. And so my picture usually involves a plane, because I'm like, this is a plane, so here's my plane. I have 6,000 passengers, so I'm going to just draw some people here. And so 6,000 people, right? So you write people if you want, or just leave it. It doesn't matter as long as you know what it is. And then over here, I have paying $200 each. So each paying $200 to fly in that plane. So $200 each. It's hard to write on this tablet. So $200 each. And then what? And then it says, the survey says for a $1 decrease in tickets, so if you go down $1, something happens basically, right? So we take $1 and we go down. What does this imply? Right, this implies that we'll gain 50 people, so we'll go up by 50 happy people. Right? They're very happy. And we want to determine the ticket price that maximizes the airline's monthly revenue. So find, let's write down what we need to find because that's usually the most important thing. It tells us what the next step is usually. Find price max revenue. That's enough for me. You might want to write more if you want, but that's all I need. So find price max revenue. So my equation, what I need to find a revenue equation. And then I'm going to search for that price. So I'm going to make a little table, basically, because I know some things, and I have an input value and an output value. So I'm going to let x be the number of $1 decreases. And there are all kinds of ways of this. So x is defined to be the number of these things, $1 decreases. So when x is 0, you're going to get out some revenue, r. And so if you have 0 $1 decreases, what you know is you have 6,000 people, each paying $200. So over here, you can write 6,000 if you want, times 200. And that's your revenue. It's 6,000 people and $200 per people. When you multiply it, you'll get dollars back. I don't really care what the actual value is, but I need to find the form because I want to find the formula basically. And then if I can find the formula, I can graph it and find that maximum. And then that should lead to the ticket price I need to charge. So let's now pretend like x is 1. So what does that mean? You made one $1 decrease. And so what happens to the 6,000? So 6,000 passengers becomes 6,050. Basically, you add 50. Then what happens to that 200? Well, you went down $1. So that 200 becomes 199, or 200 minus 1. You don't want to do the operations or the calculations because you'll lose the form. So it'll be hard to discover the formula. So now what happens with 2? Right? 2 what? So 2 $1 decreases. Well, you get the $50 from before, 50 people from before, plus another 50. So you have 6,000 plus 50 plus 50, or if you want, 50 times 2. Then over here, instead of going down just $1, you went down 2, so 200 minus 2. And you're going to start seeing a trend or a pattern occur. And once we see the pattern occurring, things become really obvious as to what the formula actually is. So let's do one more and then we'll basically have it. So what happens when you do 3 $1 decreases? Well, you have 6,000 to start with, and you go up 50, not once, not twice, but 3 times. So 50 times 3. Then you start with $200, but you did 3 $1 decreases, so you don't go down by 1 or 2, you go down by 3. And once you see the pattern, now you can do it for x. So what happens if you have x? $1 decreases. Well, clearly you start with 6,000. You add 50, and then you can see the pattern. Here you can put a 1, and so if you have 1, you have 1. If you have 2, you have 2. If you have 3, you have 3. If you have x, you just put in x there. And then left parenthesis, and you have 200 minus. And so now what goes here? Well, you see, if you have a 1, you put a 1. If you have 2, you put a 2. If you put 3, you put 3. If you have an x, you put an x. So your brain can identify that there's a form, and then you have to work with it a little bit to establish the formula. But now I know that the revenue function, r of x, is equal to 6,000 plus 50x in parentheses, and then all times 200 minus x. Now that is a quadratic function because when you multiply this out, you do get x squared stuff, although I'm not going to do it. It's not really part of the problem. The next thing I want to do is I want to create this sort of, I want to solve this, and I'm going to solve it with my technology. I'm going to solve it with my graphing calculator. So here's my graphing calculator. I'm simply going to graph this thing, so hit on, go up to y equals. Let's graph this quadratic function. So I have left parenthesis 6,000 plus 50x, in parenthesis, left parenthesis, 200 minus x. Hit the window button, and here's where I have to think a little bit, alright? So for x, I'm going to start x at 0, because that's $0 increases, and I'm going to go up, I don't know, let's go up to 100. So we could increase by 100, or decrease by $100. And let's see what that looks like. So zoom, and go to zoom fit. That'll fit the output to the input. Let's see what it looks like. So it goes up, and it comes down. I'm looking for the maximum. Ah, look, that's actually perfect. Doesn't get any better than that. So let's copy that graph down. So it started up here, came down here. I went from 0 to 100. I'm looking for that maximum, so let's punch that in. Hit second, trace to pull up the calculate menu, number 4, or if you want, scroll down to maximum. And then you can do left bound and right bound, so you can just scroll over, just hold it usually. That's definitely to the left. It goes up, somewhere up there I'm hitting a maximum, I don't know where, but I'm to the right. Hit enter and then hit enter for a guess, and out pops my answer. So it looks like my answer is x is equal to 40, and then this is 1,280,000. So here you have 40, comma, 1,280,000. Looks like that was the answer I came up with. Alright, so now what? What do you do with this information? So now I know that the input is 40 and the output is 1,280,000. So remember, the input is the x stuff, and the output, even though it says y on here, remember it's not y, it's actually r. It's for the revenue. So I don't care about the revenue. What I want is I want to find the ticket price that leads to the maximum revenue. And you have to be a little bit careful because it's not 40. Remember what X is. The input is not the amount you paid for the ticket. It's actually the amount you went down on the original ticket. So the original ticket was $200 and you went down $41 decreases. So minus 40, which is $160. And that's my answer. So if you charge $160 in this case, you will get the maximum revenue of $1,280,000. Okay, and so I think we're done. All right, so we talked about all this stuff, quadratic functions, and what they are, the tables, graphs, formulas, and then we looked at some models.